You're piloting a solo expedition into the deep stellar reaches. Ahead, there is a specific coordinate where the background stars simply stop. Mission Control is tracking this zone. Every probe that enters fails to send a signal back, and light doesn't reflect off of anything inside it. It is a region of space where matter disappears without a trace. To understand why this patch of space went dark, we have to travel back and look at what was there before it collapsed. This void is actually the final remains of a star that reached its breaking point. To understand how a star vanishes, we have to start with gravity. On Earth, we feel it as a downward pull, but it's actually a universal rule. Any object with mass pulls on all other matter around it. The more mass an object has, the stronger that invisible pull. A massive planet exerts a much stronger tug than a small moon. We are steering our ship toward the site of a dying giant star. Here, the mass is so extreme that the gravitational pull is magnified millions of times compared to our home planet. The explosive death of a star like this is the only way to witness the birth of a black hole, the heaviest object in the universe. A star stays alive through a constant tug-of-war. Nuclear fusion creates an outward push, these blue arrows, balancing the red arrows of gravity pulling inward. When fuel runs out, gravity wins instantly, crushing the star into a microscopic, ultra-dense speck. This collapse triggers a supernova explosion, blowing the star's outer layers into space. What's left is the core, squeezed into an infinitely dense point called a singularity. We now have an object with so much mass in such a small space that it breaks our standard understanding of how physics should work. This new object appears pitch black because its gravity is now so intense that light, the fastest thing we know, cannot move fast enough to escape its pull. Here is the anatomy of a black hole. The heavy dashed line is the event horizon. Anything crossing this boundary is trapped forever. Outside, matter is whipped into a swirling wing of superheated gas called the accretion disk. The event horizon acts as a permanent gatekeeper, isolating the interior of the black hole from the rest of the universe. As we fly closer, the intense gravity bends the light of the stars behind the black hole, stretching them into distorted arcs around the sphere. General relativity tells us that mass doesn't just pull on objects, it warps the very fabric of space and time. Because the curve is so steep here, time itself slows down. Your clocks tick much slower than they do for observers back on Earth. If you move any closer, the gravity at the front of your ship will be much stronger than the gravity at the back. This difference would stretch your ship into a long, thin noodle, a process scientists call spaghettification. We have to fire our thrusters now. By pushing against the pull, we can just barely escape the gravitational drag before we hit the point of no return. Surviving a flight this close is the only way to gather data on the edge. It proves exactly why the event horizon is the most dangerous boundary in the cosmos. While stellar mass black holes are scattered throughout space, supermassive black holes live at the center of most galaxies, acting as gravitational anchors for millions of stars. We can detect these invisible objects by watching their neighbors. We look for stars that are orbiting at incredible speeds around a point in space that appears to be empty. The glowing accretion disk provides another piece of evidence. Using a global network of radio telescopes, we can capture the light being bent into this asymmetric ring, revealing the shadow of the black hole itself. By tracking how these objects manipulate the stars and gas around them, we can use the data to assemble a physical map of a region that reflects no light. As we head back to Earth, it's worth clearing up a few common fears. Our sun will never become a black hole. It simply doesn't have enough mass to collapse that far. Black holes also don't wander through space like cosmic vacuum cleaners. From a safe distance, their gravity acts exactly like that of any other star or planet. Earth is perfectly safe. The nearest black hole is thousands of light years away from our solar system. Even so, one mystery remains. While we can map the edge, the singularity at the center is still a point where our current laws of physics stop working. That unknown territory is a puzzle waiting for a new generation of physicists to look at the stars and ask why.